Yeah. So we've been talking about big O on and off, kind of touching on it, but not really going into detail. So would anyone care to tell me what they know about big O?
So I think it's a means of evaluating how much time or how the time a function takes scales with the amount of input that's given to it. So like, I know that you were talking about like O of 1, which is like constant time. So independent of how big the data set is, it's always going to execute in the same amount of time. Then O of n means it's linear. So increasing the input increases the output by 1. And then O of n squared would be like if you increase the input by 1, its output is like squared. So
Yeah, exactly. So it's kind of a, in some ways it's a strange way of thinking about code, but it's a way of abstracting a lot away from the code. So you might think that what you want to do is just time your code, right? So how do I know if one function is faster than another one? Well, I'll just time it, and then whichever one runs the fastest is the fastest. And that makes sense, and that that can certainly be a part of how you tell. But the problem is that it's difficult to communicate about that. So, I mean, you could come up with a standard where everyone times their code on the same hardware with the same software and the same processes running in the background, and the same state of solar flares and whatever else will affect how quickly something gets processed. But it's very difficult to do. It's too messy. There's too many variables. So if you want to talk kind of sensibly about these things and compare them, you need a way to abstract away from all of those nitty-gritty details that are going to vary from run to run. So let's look real quickly at a kind of, let's say, naive approach. So you have to ignore the quotes. You'll see why I'm doing that in a sec. Kind of giving the game away by calling this naive.py. But so we could ask which one of these functions will run faster. This one where I assign a to x, or this one where I assign a whole bunch of stuff to x. So you might wonder, okay, is this one faster than this one? Maybe. I mean, we might think about, take a guess, make a hypothesis. So probably this one is going to be faster than this one, just because there's, less involved seemingly. And we could test this actually by we're going to run it a whole bunch of times. Import time it. So time it is a built-in. It's basically used to time your code. So it's not like timing your code is bad or anything. But it's a bit weird. It can take a string, takes a string, and then how many times you want to run your code. So what we can do here is let's just run it. And so we ran it the first time. So the first one ran in 0.074 seconds. And this ran like a million times. It ran this a million times. So let's run it again. I'll just comment this out. Okay, so now that time that was about the same, like 0.070. Okay, and this one is slower. And now the first one is faster and the second one is slower. So there's all this little there's all this variation, and maybe if we like investigated this enough, we might find that one of these is in fact faster or slower. If we run this a whole bunch, it looks like maybe the first one is faster. But again, like, how do we talk about this? Is this, you know, is this 2% faster, or does that make a difference? There's so much variation and noise here that it's hard to say anything very meaningful. So one thing that we talk about, or one thing we don't talk about when we talk about big O, is stuff like this. So we basically don't care about the difference here. For one, we're not really going to talk about memory complexity, but just talk about, excuse me, we're just going to talk about runtime complexity. So if to us in big O terms, these are the same. These are both O of 1, meaning that every time I call this function, I perform one operation. So how fast does it actually take? Does it take, you know, a millionth of a second or 2 millionths of a second? That difference doesn't really matter to us. Okay, so let me show you this graph. I think this is a very good graph. This is from bigocheatsheet.com. So here's a chart showing basically big O runtime complexity. So this graph is not really proportional. So O of n, it's not proportional so that it can show you these extreme cases over here, right? Otherwise, this O of n line should kind of be like right in the middle. But this is linear. So O of n, so as the number of elements increases, as I increase the number of elements by 1, the number of operations I have to do increases by 1. O of 1 is constant time, so it doesn't matter how much data I have. O n log n, this is most of the best search algorithms. This is basically as good as you can do with a search algorithm. O of n log n, and then once we get over here, we're looking pretty bad. So O of n squared, this is every time I add one more input element, I square the number of operations I perform. So if I have 4 elements, then I do 4 squared operations. If I have 5 elements, I do 5 squared operations. And then this is O of 2 to the n. So this is really, really bad. And a kind of simple, well, yeah, we'll look at some examples for all of these. But so this is, if I have 5 elements, then I do 2 to the 5th operations. And if I add one more, I do 2 to the 6th operations. So this rapidly increases. So big O is very abstract. It abstracts away from all these low-level details. And part of the reason it does that, and that it can kind of get away with that, is because it only really cares about huge numbers. So big O is built for n being very, very large, not 2 or 3 items or 10 items, but like a million items or a billion items. That's when it really becomes important. So if you're performing some kind of operation, a function, whatever the case is, and your input size is 50 and it takes you however long it takes you, that's fine. But the issue is, what happens if I increase that to 1 million? then how much more increase in time is there going to be? So you can easily go from something that is, you know, doable to something that is basically impossible. So we saw, for example, the Sudoku Solver. So my first naive implementation was basically to randomly generate a bunch of numbers, then randomly check all of them. And that time complexity, I don't even know what that would be, maybe O of n factorial, testing all possible permutations. So after about 4 or 5 blanks, if you have more than 4 or 5 blanks, it basically becomes impossible. It would take forever to solve, just because it shoots up so immediately and so drastically. Okay, so we have all this stuff. Let's kind of maybe get a little bit more specific. So why is this important? So we have all of these different data structures. And you know, why do we have all of these different data structures? Well, part of it is because they're all kind of good at some things and not so good at other things. So just in terms of time complexity, if our prime goal is to access stuff quickly, then we should use an array, right? Because we can access stuff in O of 1 time. So again, if we have 1,000,000 items in our array and we want to access the 10th item in the array, it takes the same amount of time. If we double now we have 2,000,000 items in our array and we want to access the 10th item, it takes the same amount of time. So the number of operations you have to do is independent of the size of your input data for O of 1. Now, of course, that's not true for other operations like search. So if you want to search through an array, an unsorted array, you basically have to use linear search. So again, if I have 1,000,000 items in my array and I want to check for a given value, I potentially have to look through every single item in that array. So you might get lucky. You might get lucky and find it, and you find it at index 0, right? But that doesn't mean that your algorithm is O of 1. Just because you happen to find it quickly in one iteration, that doesn't mean your algorithm is O of 1. What you care about almost always is the worst case scenario. So what is the worst case scenario? So in terms of linear search, the worst case scenario is it's not there. So you have to look through every single item in the array to find that it's not there. So search is O of n. What about for a hash table?
So it's faster for search and search than a deletion, but it looks like it can't be accessed.
Yeah, I'm not sure why it's an access.
Okay.
Yeah, maybe just search is access in that sense. So there's also a worst case. So over here is the worst case. This is average case and worst case. So we didn't really go into it, but if you have a lot of collisions, then potentially you could be like using the same hash key and then building on it. So it would just be like creating an array basically. So depending on implementation, so that there are all kinds of complexities here. Okay. So things like this is just something you want to think about when you're choosing a data type. What are the common operations I'm going to do, or what are the most important operations, or what operations are going to be a bottleneck for me, and then choosing an appropriate data structure based on performance characteristics. Okay. So let's go ahead and we'll look at a couple examples, I think. So O of 1. O of 1 is going to be something like get the first item in array. So we can take a look at that. So right, so if I so if I have this array and I have this function, and this function is always going to return the 0th element of an array. If I pass in nums, let me get some stuff going here. All right, so I'm going to here's a timer decorator that I'm going to use to decorate some of these functions, just so I don't have to keep writing the same thing over and over again. So it's just going to start the timer. So it's from this time it module, and it's going to call the function, and then it's going to get the end time, and then it's going to return basically whatever fractional milliseconds it takes times a number that makes it readable. All right, and then I'm going to decorate this. And then I'm going to print this. And we'll see again. So we'll see that, it took however long it took. Not very long, of course, right? Now the question is, what happens if we, so now our input size has increased by a factor of 10. We run this again. So let me just run this again. So again, we don't really care about the specific time. So the fact that this, is however many like thousandths of a millisecond, and this is a little bit more, that doesn't matter to us. We've increased our input 10 times and haven't really nudged significantly our time. So even if we make this very large, might take a second to get. Let me try that again. Make that a little smaller. So you see how much variation there is, but from going from 10 to 100 to 10,000 doesn't really have much of an effect. Right, so this is O of n. Although it's very messy, we can basically say that this is O of n. Or sorry, O of 1, I bet. All right. So the next level up would be something like O of log n. And this would be something like binary search, where we're having our input every time, right? So if we get 100 items, we're going to have it, so it'll be 50, and we're going to look, and then if we do another search, we're going to have it again to 25, and if we have it again, we'll go to whatever 12, and half it again, and so on. So every time you run through, we're dividing it in half. So if we increase our input by 1, we're increasing the number of operations we have to do by some fraction. So it's more than, it's not constant, it's not O of n, but it increases very, very gradually. So yeah, that's an example. O of n. So what's an example of an O of n operation?
Regular search through an array.
Yeah, so something like linear search. Right, so we can do, let's see. Yeah, I'll have some plotting stuff here in a second, but for now we'll just do this. So I'm going to we'll do linear search. So I'm going to put in -1 so it won't be there. So I get the worst case every time. So 4. So something like that. So I'm going to take an array and then I'm going to check every single item and compare it here. So let's do let's start with something small. 100. So 0.04. So, it's not exactly 10 times more, but it's something in that ballpark, right? It's like 6 something times more. And there we go. It's 6 times. Yeah. So, so there's a lot of variation, but we can say that it's roughly linear. If we add some, we're going to do a corresponding large number of operations. Now, of course, we're not actually measuring the number of operations, or measuring the time, which is kind of again a rough proxy of the number of operations. So Another issue here is, what do we count as an operation? So here's something, let's try doing this. Okay, so now we have, so this is not really linear search anymore, but so we have a function, and we take an array and we loop over it, and all we're doing is assigning, like reassigning this, and we can see that it seems like it runs faster, maybe. Seems like it's even like twice as fast, right, as the other one. So on the other one, remember we had, conditional, and we're doing a little bit more stuff. But we don't care about that because it's it's constant, right? So it's basically a coefficient. So if you are into math, like I am not, so don't ask me too many detailed questions about this. But if you are very into math, you can look this stuff up, and they're all kind of formulas, and it's very complicated. This is a very stripped down version, and even like properly speaking, all of this big O notation, it's stripped down. So things like coefficients are removed. So we only care about the stuff that really is going to impact the performance of this at a large scale. So so the number of operations we're doing here, let's say if we have 10 things in our array, that this for loop is going to run 10 times, right? And then we're going to assign this 10 times. So in some sense, that's like, okay, isn't that 20 operations? But again, we don't care about that because it's the same. So if this is 10, we do 20 operations. If this is 100, then we do 200 operations. And if it's 1,000,000, we do 2,000,000 operations. So we don't care about that because it doesn't change, and it doesn't bring us up another order of magnitude. So even though in the real world it means something, right? Adding a bunch of if statements, it takes time to execute, but we still don't really care about that. And if we added a whole bunch more if statements, it would take longer. But it's still basically, even if we add 10 other if statements in here, and so let me just do some of that. Something like that. This is just nonsense, but I'm adding more checks. So now every time I loop over, so there's one operation, 2, 3, 4, again, worst case scenario, right? So worst case scenario, I'm doing 4 operations for every time through this for loop. So if I have, again, 10 items, then I'm doing worst case 40 operations. And if I have 1,000,000, I'm doing 4,000,000. But it still scales up. It still scales up in a constant way. Okay, So there are other, there's a O of n log n. We can do. Are there any questions about so far? So O of n log n, this would be something like merge sort. And this is the best. So I'll also say that we basically only are going to care about 3 of these. We're going to care about O of 1, O of n, and O of n squared. And those are really the big ones. So O of n log n, this will be merge sort. So it increases faster than, it's not linear, but it's not quite as bad as quadratic. So O of n squared. So can we think of a quadratic function?
If you have 2 for loops nested inside each other.
Okay. So let's do something like, what could we do? All right, so we'll do something like this. Doesn't really matter what we're doing, but let's just say we want to get every possible combination of 2 things in a list. We'll create a new list. And then we'll return combos. So we're going to return an array of combinations. So we're going to loop over this list twice. So for every single one, every single item in the list, we're going to check it against every other item, including itself in this case. And then we'll create a tuple, and then we'll append that to combos. And then at the end of that, we'll return all of them. So let's go back up to nums. So now nums has a length of 10. So how many operations are we going to perform when we run this? When nums is 10.
100.
Yeah. So we'll actually do more than that, but yeah, that's what we care about. We care about 100. Again, we don't care about the time. So let's just say, now we'll, 10 times the, and that gets us 100 times the time, right? So every increase, so if n is 5, then we perform 25 operations. If n is 6, we perform 36 operations. So of course, if we look here carefully and think about all the okay, so here we're assigning an array to this variable. So that's an operation, right? Here, every time through this for loop, this n1 is going to get reassigned. So that's another operation. And then here, again, inside this for loop, this n2 is going to get reassigned for every item, for every single item in nums. And then we're going to do another operation, or even two operations. So we're going to create a tuple, and then we're going to append that tuple to combos. So we're doing a lot of operations, but again, the bottleneck here, or the thing that really changes the game fundamentally, is this inner for loop. So we don't care about nickel and diming. We're looking for like radical shifts. So if our input goes from 100 to 1,000,000, this is going to take significantly longer, significantly more resources than an O of n algorithm. So nested for loop is usually a good sign of O of n squared. So let's look at another example real quick. Okay. So set it at 100. So what do we think about this one? Would someone like to analyze this for me?
I'll give it a try.
Okay.
I think the n in 3, 4, 5 is pretty much constant time because there's only 3 operations all the time. So that should be order n, which would be that coming from the first for loop.
Okay. Well, what if I do 3? So passing in 3 items here.
Then that would be n squared.
So it would be n squared for 3. And what if I pass in 1,000,000 items?
It would be 1,000,000 because it's constant. It's like a three items. It's a constant. So the n
Yeah. So
overshadows it.
Exactly. So even though we still have a for loop within a for loop, this is a constant. So if our n is very low, like 3, it looks like that this is O of n squared, because that's actually what it is, right? It will run 9 operations. But the question is, what happens when you increase nums? So when you increase nums to 1,000,000, this becomes insignificant, right? So we're not talking about O of n squared anymore. We're talking about O of n times 3, which is a much, much different ball game at a large scale. So even though this is not nothing, we can basically ignore it when we talk about big O notation. Okay. Yeah, so that would be something like whatever we were doing. Permutation, I'm sorry, I don't know statistics. Permutations, combinations, I don't know the difference. One of them is replacement, one of them. Anyway, so what were we just doing? So that's quadratic. And then, okay. So are there any questions about the base? So what you need to care about here is O of n squared, O of n, and O of 1. Well, 1 is constant time. It doesn't vary. The size of your input is irrelevant. Here, the size of your input, there's a 1-to-1 correspondence between increase in your input and increase in time complexity. Here, we're in kind of dangerous territory where increasing your input will, you have to you square the number of operations. Okay, are there questions about this? All right, let's look at so I've just set up a little something here. Not really well written. You'll have to excuse me. All right, so let's take one of our yeah, we'll take this one. Let's see. I think this should work. All right, so what we're doing is we have a whatever function we want to test here, and then this is going to be a bunch of different input sizes. So the particulars doesn't really matter, but kind of somewhat random, just a bunch of different input sizes, and then we're going to time the function. So we'll start and stop this function. We'll take data as well. So we'll create a random data set to pass in. We will start, we'll call the function, we'll end, and then we will append the interval. So if we had 10, so 10 items, interval is probably a bad name. We do, this should probably be called n. We'll append it, and then we're just going to graph it. So I do not have a virtual environment set up, so let me create one. So to create a virtual environment, let's see. Jim, could you tell me how to create a virtual environment, or at least approximately, if you don't remember the exact syntax?
Yeah, I think so. It's the VM, so it's Python-m, and then you can call it like big O. Oh, yeah.
Okay. So yeah, we'll run the ven. So ven is in the standard library. We'll run that as a module with the -m flag, and then we can call this whatever we want. So big O ven something. So now we've got that over here. That's created. So what should I do next?
You need to source it as your, so source big O env, yeah. And then inside of that, it's the bin and then activate.
So this is going to run a script and basically apply it to our current terminal session.
Yeah.
So
and then
now,
you can use pip to install your packages.
Okay. I'm going to install something called matplotlib. Kind of like a standard graphing library. Okay. And go. So let me try running it one more time. But so you can see that again, this is very chaotic, the timing. You can see that as the number of as our n increases, you know, seemingly it shoots way up right here, but these are just kind of random spikes that probably have to do with what other processes are running on my computer. So you can see that there's not really a trend here. It's basically sticking around. It jumps around, but it's pretty steady. So let's run it again. So again, we get another very random distribution. Let's try running it one more time. So looks pretty random. So again, it like one, it's extremely high, and then it's all over the place, which is why we don't really rely on actual timing. We kind of use this big O abstraction, but this is O of n, so this is constant time. Okay, so here's constant time functions. This is O of 1. Sorry. So O of 1 doesn't matter how big our input size. There's not a consistent trend. All right, so another thing we could do, let's look at our other example. Do linear search. Yeah. I'm just going to get rid of these. So let's try running this. And here, when we graph it, we see something more like a trend, right? Again, it's not perfect, but this is at one, let's say 1,000 operations. It's roughly 3.5 seconds or whatever units. And at 2,000, it's roughly double that. We can run it again. Again, just different, but we can still see that there's a trend. I'll run it one more time. So again, spikes, but you can still see that there's a trend. So that's O of 1. Or sorry, geez, that's O of n. All right, and then we'll look at O of n squared. The O of n squared function was
Chad,
yes.
I have a quick question on that, just on the code.
Sure.
What's the R sub 1? If you're always grabbing like, oh, never mind. All right, I answered my own question. Yeah, it's a tuple and you're grabbing the first element of
Yeah.
the tuple. Yeah. Okay, thanks.
Okay. All right, so here's our O of n squared. Of course, it takes a little longer to run. You can see there's a little bit of a curve here, right? So when we double, our first doubling from, let's say, 250 to 500 doesn't do much. But if we, 1000 is, let's say, 0.2, 2000 is 0.8. So there starts to be a big difference, and the higher it gets, the more dramatic that difference becomes. Let's run it again. And you can see that curve there, and that will just go higher and higher and higher. So I think the main takeaway from this is you want to try to keep things below O of n squared, because that doesn't mean it's always possible to, but it's very difficult to scale O of n squared stuff.
Are there like static code analysis tools that review your functions for this? I saw there's some big old libraries out there.
That's a good question. I actually haven't looked into that, and I haven't seen it anywhere, but that's a good question. So I will say that although we're talking about optimization, most of the time you don't need to really worry about it. So you need to worry about it for interviews and just for your general knowledge as a programmer. But in terms of like on the job stuff, you almost never actually need to worry about optimization. And if you do, you should measure your system. You should take metrics on your system first, so you know where to optimize, because almost always there's going to be some kind of specific bottleneck. So if you just go like randomly optimizing stuff, probably it's not going to make any difference. So let's just say, for example, you have a standard web application, and almost always the bottleneck is I/O operations. So talking to servers, right? The processing time, if you have a web browser, your web browser spends almost all of its time just sitting there. And then it maybe does a little bit of processing, makes a request, then sits there and waits for the request. And the request comes back, does a little bit of processing, and then just sits there. So there's a lot of dead time with the browser. So if you wanted to optimize a web application, the biggest bottleneck is I/O. So what high-end applications and stuff do is they set up all these like proxy servers and stuff like that. So that's really where the big optimization. So you have what can't I think of the name? CDNs, content delivery networks. There's a lot of caching and things like that. That's how you increase efficiency in a system like that. So if you go around just kind of, I'm going to have the most efficient, whatever for loop here. If your application, let's say from start to finish, your application takes 2 seconds to run, and this particular function that you have that you make super efficient, it shaves off, a couple milliseconds. That's not really significant to the overall application. So the basic idea is like, yes, you have to learn this, but again, it's one of those things you need to learn because you need to learn it for interviews and for your general knowledge, but don't fret too much about it, because it's probably not going to be a daily problem for you, a daily concern. Okay, are there any questions about that? All right. So the challenges for today, basically, there are a couple problems asking you just to think about, here's a function, what's the runtime complexity? And then reviewing your previous solutions to things and analyzing them in terms of runtime complexity, and maybe seeing if you can come up with something more efficient. or if not, at least be able to talk about it. So that's, again, for interviews, it's a common follow-up question. I mean, you can basically assume that, okay, here's my algorithm solution, and the runtime complexity is O of n squared. So even if you can't fix it, because fixing it's not always just like easy to fix it. Oh yeah, it's n squared. Let me just go ahead and make this run a lot better. So sometimes the fix is pretty easy. Oftentimes the fix involves trading memory for speed, and sometimes it's just some kind of trick involved. All right.